Following up on the noise distribution we just discussed, let's take a closer look at this formula for the total input referred thermal noise, NT. This equation really dictates our design strategy. First, let's consider a straightforward approach. What if we just make all the sampling capacitors the same size? So, C1 equals C2, C3, and so on all the way to Cn. What happens then? Well, look at the terms in the equation. The noise from the first stage is proportional to 1/C1. The noise from the second stage, when referred back to the input, is proportional to 1 over G1 squared times C2. Since the stage gain G1 is greater than 1, G1 squared is even larger. This means the noise contribution from the second stage is significantly suppressed. And for the third stage, it's divided by G1 squared and G2 squared. So, the further down the pipeline we go, the less noise the back-end stages contribute to the overall input referred noise. The first stage is clearly the dominant noise source. Now, that might sound good at first, but is it an efficient design? The slide points out that it's actually wasteful. Because in these switch capacitor circuits, the power consumption is related to the size of the operational amplifier, which is determined by its transconductance, Gm. And Gm is, in turn, proportional to the size of the capacitor C it needs to drive. So, if we use a large capacitor in every single stage, we're also using a large, power-hungry op-amp in every stage. But we just saw that the noise requirements for the later stages are much more relaxed. We're essentially over-designing them and wasting a lot of power. This brings us to a much more elegant solution, stage scaling. Instead of using identical stages, what if we strategically make the later stages smaller? The slide proposes scaling by a factor related to 2 to the power of m, where m is the resolution of each stage. The idea is to shrink the capacitors in each subsequent stage. By doing this, we can achieve two very important goals. First, we can design the circuit so that each stage contributes a more or less equal amount of noise when referred back to the input. We are balancing the noise contributions across the pipeline. Second, and this is the huge benefit, because power is proportional to capacitance, by making the capacitors in the later stages smaller, we directly reduce their power consumption. This allows us to significantly cut down the total power of the entire ADC without compromising its noise performance. It's a classic engineering trade-off, optimized for the best overall result.